test the connection before your opposition starts. Yeah. Okay. We finally are at the end, like stage 4. We have Team Taiwan as reviewers and Team Kazakhstan challenging Czechia on problems that are written on the whiteboard. So you can challenge only on those 8 problems, Team Kazakhstan, like 1, 2, 5, 6, 7, 8, 15, 16. And we can start the clock and we can start the challenge procedure.
Challenge you on the task number 16, weird spot.
We are start. Problem number 16, which compensates.
It's okay, I will go there. It's okay.
1 minute left.
Good afternoon, everyone. I'm Lukáš from Czechia, and this is the Virts pump. We are to investigate the maximum pumping height of a Virts pump depending on relevant parameters. So on the video we can see how a real live Virts pump works. So let's start with the state of the art. Virts pump is a old pump, and there was a theoretical model created in the literature, but there was no experimental work published on the Virts pump. So our goal will be to improve the theoretical model from the literature, create a repeatable apparatus to make the measurements, and experimentally validate our improved model. So let's start with why the Virts pump pumps into such a great height. There are two phenomena overlapping. The first one is that the pressure in the Virts pump is stacking because the water segments are aligning such that they are creating pressure. And the second phenomena that is present in the Virts pump is the water lift. And water lift is a phenomena when there is the mixture of air and water in the vertical tube that is in which the Virts pump is pumping into the great height. So when there is the mixture, the average density of the liquid decreases. So now let's look at a Virts pump with no air lift. When the Virts pump is spinning, it's intaking water, and here there are water segments that are creating the pressure. So the water is rising. When we add up those heights that the Virts pump that are in the spirals of the Virts pump, we can add them up to the height into which the water rises. So let's start with the state-of-the-art hydrostatic model. There is a model that predicts the alignment of the water plugs in a Virts pump, but it has one unrealistic assumption, and that assumption is that the length of the first water segment and the first air segment, which is under atmospheric pressure, is equal to the length of the first turn of the spiral, which, as you can see on the picture, is unrealistic because here the Virts pump would be in reality already intaking water. So we must modify the model such that the air segments are dependent on the initial condition of the first plug of the water, so that they and the water level, and they have the realistic length. So let's look at the overview of the theoretical model we will be using. We have two values we have to know from the experiment: the pump geometry and the rotational speed of the pump. From the pump geometry, we calculate from the hydrostatic model the air and water plug lengths and the pressure at the end of the pump. Using the air and water plug lengths and the rotational speed of the pump, we calculate the viscous pressure loss in the fin tubes of which the Virts pump is created, and we subtract the pressure loss from the pressure at the end of the Virts pump. From the pressure after subtracting and the air plug and water plug length, we calculate the airlift, and from that we get the maximum pumping height of the Wirtz pump. So we will start with the hydrostatic model. We take the hydrostatic model from the literature, adjust it, that the hydrostatic model takes the pump submersion depth to get the length of the water segments and first plug position. So first plug position from the pump submersion depth we get the water plug length, and the air plug length we are getting from the initial condition of the first water plug position and we calculate the length to the water level we get from the geometry. From the initial condition of the position of the first water segment, we are getting the difference between the height of the ends of the water segment. From that we are getting the pressure that this water segment adds to the Wirtz pump, and from this added pressure we get the next air plug length because it gets compressed by the added pressure using boil saw, and then the next water plug. From that we calculate the next water plug position because it will be after the air plug, and we repeat this process until we go through the whole Wirtz pump and get the pressure at the end. So now we will continue with, sorry, I forgot that we have to do this for every position of the first water plug, and we take the maximum pressure and we do this for all the first position of the first water plug, and we calculate the maximum pressure. Now let's continue with the viscous pressure losses. So there are two places where the losses can occur: in the spiral of the pump and in the airlift where the water is going up. We calculate the losses in both, but we found out that the losses in the airlift are much greater because we use a tube with smaller diameter. We calculated by the standard formula for laminar flow because the Reynolds number is 2000. And we calculate the flow rate from the RPM of our pump. When we compare those three models, we can see that there are quite a large differences in them. We can see that between the model from the literature and the model with fixed air plug lengths, there is a big difference, and even adding the drag helps to decrease the pressure at the end of the Wirtz pump. Now let's look at the calculation of the airlift. We calculate the airlift iteratively by starting with a water segment at the top of the airlift. We know the length of this segment from the hydrostatic model and the geometry of the pump. Under that we add the length of the water segment, which is compressed by the water segment above. Under this we add another water segment, then another air segment which is compressed by the two water segments above, and we go like this iteratively until we get until the pressure from the airlift is equal to the pressure of the Wirtz pump of the hydrostatic model. When we compare the models with the airlift, we can again see a great difference. So let's look at our apparatus. We made a Wirtz pump that was vertically held. That was held on this apparatus. There was a motor that was turning it with a constant RPM, and the vertical tube was on the staircase above. We always place the water tube such the pump is pumping to a bucket, and we are trying to find the maximum for the geometry we are using. We used a pump with 7 turns, and the diameter of the pump was 69 centimeters, and then are some other parameters. We used colored water, so it is better for visualization. So were trying many different tubes for the Vince pump, and we settled for 4mm pipe for the airlift, so that the segments will hold and not hold, and we wanted the 4mm also for the spiral, but that was not possible because this thin of a diameter had problem with intaking water, so we settled for the 6mm tube. When we compare our model with the experiment, we can see a really nice fit of our measured values with the theoretical data. For smaller submergent depths, the water segments are shorter, so they cannot hold as good as the longer ones. So for this experiment, the water segments didn't behave ideally, so the airlift wasn't ideal, and we lost some height due to that. So let's discuss some other relevant parameters. We already mentioned the submergent depth and its importance, and we did measurements for this. Then we mentioned the varying tube diameters that have qualitative difference for our assumptions for the Vince pump. Then with increasing number of turns, our theory predicts increase height of the pump height, but the same pumping speed. For higher rotation speed, because of the viscous losses, we predict lower pumping height but higher pumping speed. And then the water parameters are also relevant, but not that much. So to conclude, we modified an existing theoretical model so that predicts the experimental data well, because we added a realistic condition and added viscous losses. We created a repeatable and functioning apparatus that was able, with which we were able to measure repeatable experiments, which confirmed our theoretical prediction, and we established the relevant parameters for the Vince pump as the task was asking about. Thank you.
Thank you.
Thank you very much for your presentation of the Vince pump. So my first question to you, did you consider any type of the spiral?
So we use the Archimedean spiral.
Only Archimedean.
Only.
Okay. So what do you think about the most important parameter for the pump height of the system?
It's hard to say the most important, but the two most important is the submergent depth and the number of the turns of the spiral.
And any parameter which you consider?
Sorry?
Do you have any parameter which you consider in your system?
Yeah, we considered those two.
No, any parameters except that.
Any parameters except that?
Yeah.
The pump rotation speed was considered in the viscous
Okay, and thank you very much. And how do you control the rotation speed?
By a motor.
By the motor. And so do you have an experiment for the checking the angular velocity?
No, we didn't change that.
Yeah, because there is an increasing of the mass of the water inside the spiral due to the time. Okay. So did you calculate the viscous friction first, accounting to the motion of the water flux?
Yes, we counted the viscous pressure law, so that was one of the three parts of our theory.
Okay. Okay. So the next question to you: Are all the water flux lengths are same?
Sorry?
Are all of the water flux lengths same?
Yes. From the time symmetry of the problem, the Vince pump is spinning, and it will be
the topic for discussion. And so, did you consider the centrifugal first?
No. With 6 RPM, the centrifugal force is really.
But there is a pressure gradient due to the spiral. Okay. And so, did you open the? Can you open this 70 slide?
17?
Yeah, 70. Okay. Do you have any experimental evidence for these conclusions for for
No.
this hypothesis?
It is really hard to do it is really time consuming to do experiments with the wet spam because it is
Okay.
really hard to.
Okay, yeah, you're right.
Thank you. Preparation time for this? Classical music sounds a bit nice.
Checking of the
No, just
errors.
Guys, we should start.
Okay. Hello everyone. My name is Dimuhan Akhitar. I'm the representative of the opposition team for the 16th problem with pump. And there is a problem statement. A wrist pump is a hollow spiral mounted vertically. It's arranged such that one end dips below water once per revolution, while the other end at the center of the spiral is connected to the vertical tube. When rotated, it can be used to pump water to a great height. Explain this phenomenon and investigate how relevant parameters affect the pumping height. And so, first of all, I want to start from the expectations from the report and from the work itself. First of all, I want to start from the quality of explanation of the pumping process and how the water flag increase their height from the one turn to the next turn, and how the water flag can transit to the vertical tube at the center of the spiral. The second one, I want to listen to about the reason of the height instability. That in the vertical tube, there you can see here in the graph of the report, there is instability of the height. The second one, the dependence of the pump height from the relevant parameters. A comparison in theory with the experimental results itself. Upper right approach to the measure pumping height, the maximum height conditions, and the consideration of the air bubbling, overflow, and the flow assistance with the phenomenon which can be considered in the spiral. Let's go through the strengths for the report. First of all, he accounted for the surface tension and the counting of these energy loss has a big effect on the pumping height. Investigation on the frequency dependencies on the water. Set the nice setting of the experiment. Study some relevant parameters such as viscosity and the tube diameter and the number of tubes. And the submersion depth. But there is, of course, the areas for improvement. First of all, I want to start with a vague quality explanation of the phenomenon and, as I said before, the quality explanation of the pumping process and how the water moves from the one turn to the next and the transition to the vertical tube. Poor time management, there is some errors and there is some mistakes with time. Lack of the experiments, you can see here that in the graph there is a lack of the experimental numbers, which is not sufficient to compare the theory with the experimental setup. And there is also the lack of the variation of the relevant parameters. Of course, he considered some relevant parameters, but there is not all. And it will be discussed in the next. So. Per scientific communication with the theory and how he didn't clarify some parameters and the slides. No pumping process, as I said before, no clarification of the theoretical models, as I said before, and the lack of the explanation of the for the errors. Didn't consider centrifugal force, which is also important as a spiral shape. Lack of the experimental evidence for the hypothesis, which he considered and said to us and the vague number of experiments. So that's the topic for discussion. First of all, I want to discuss about the experimental control, how he can control the angular velocity, the consistency of the angular velocity, and the rotation of the vertical tube. The consideration of the more relevant parameters, and the clarification of the graphs on the report, errors of the theory, water plug length, and the clarification of the parameters on the slide. Okay. So I would like to invite our reporter to the discussion.
Please start.
Okay, so I want to start from the. I would like to open the slide number 9.
Slide 9. Okay.
So okay, you can see you are explaining your theoretical model for the traditional pumping factor. Yes. As I said, as I understood.
So for the pressure at the end of the response.
Okay, and can you explain more about these parameters which you consider here, and what the effect of these parameters, and what does mean these equations?
This equation, this is the hydrostatic pressure equation, and this is the Boyle's law.
Hydrostatic equation for what?
For the pressure, because the response at pressure by the difference in height between the water segment. This is the one end and the other end.
Okay.
And the difference between the height at pressure by the hydrostatic pressure.
So you considered only the hydrostatic equation for the water, for the water plug.
Yeah.
Okay.
I don't see why they should be adding pressure in any different way.
Okay, but as I said before, there is a constant value of the angular velocity on the system. Yes, as I said. Okay, so it means that the water length here have also the dynamic pressure.
But it's spinning by 6 RPM. That's really slow. One rotation in 10 seconds.
But if you will change the angular velocity, it can be the reason of the increasing of the pressure. But
the deviation would start in a different way, because when the waveform will be spinning fast, the first problem would be with the intake of the water, which and I don't see the dynamic pressure in any relevance, because this model describes a wedge pump. A real wedge pump is running on the water stream of a river, and the trailing speed is really slow, as you can see. And we are trying to describe a real world wedge pump, but for the real world wedge pump there is no.
Okay, I heard your explanation of your the lack of the consideration of the velocity, but you said that the angular velocity is your parameter which you consider for the pumping height, yes?
Yeah.
It's one of the parameters which needs to be considered.
Yeah, because of the viscous losses.
Yes. Well, okay. So it means that there is a change on the angular velocity in the system.
the angular velocity changes the pressure at the end of the British pump because of the viscous losses. Yeah, because with higher rotational speed, the pumping speed is higher and the speed of the water is higher, so the viscous losses increase.
Okay, so in that case we have a disagreement with the reporter because the angular velocity is one of the most important parameters which needs to be considered from the pumping height, and that there will be the reason of the dynamic pressure by the water flag to the vertical tube. Okay, so I want to you to return to the 9th slide. There is another equation which you put it here, and can you explain this more? What
This is Boyle's law. We are intaking always a air plug with the same amount of molecules, but all water plugs have all air plugs have different lengths because of them being under a different pressure.
Yeah.
So they are getting shorter, and we are calculating it using the Boyle's law because the temperature in the plug is everywhere the same.
Okay, so and that's the full representation of the Boyle's law?
Yeah.
This equation. Okay. So, and again about the relevant parameters. So, can you list shortly all the parameters which you considered for the
We consider the submersion depth in the theory, the tube diameter experimentally by optimizing it.
One question. Is the inner tube diameter or the outer type?
The inner tube diameter is important. The number of turns theoretically, the rotation speed theoretically, and empirically we watched it so because we needed to check that it is intaking the water the right way and the water segments are defined by submersion depth, and then we considered the relevant parameters of the water such as the viscosity for the losses or the.
Okay, so what there is, I think that there is one more parameter which you needed to be considered, and that's the distance between the tubes. So as said before, can you return to the next slide? You said that there is for the calculation of the hydrostatic pressure, we calculate the distance between the one end of the water flag and to the next. Yes?
Yeah.
Okay. But if you will increase the distance between the tubes, between the
I'm sorry, I forgot to list this parameter. We considered it theoretically, and the Archimedes spiral constant was this.
Archimedes spiral constant. Okay.
That defines the distance between the pipes when you multiply by 2 pi.
Okay. So maybe I think that you need to append this parameter to your list so that everyone can
but
understand.
it is not really the most important parameter.
Are you sure?
When you don't do anything extreme with it, it's not really that important. It's way more sensitive, for example, on the number of currents.
I want to show that so there is some disagreements with you. Disagreement of opinions. So you said that you calculate the hydrostatic pressure.
Yeah.
Okay, so something like that. So if you will rotate the spiral to this side with the constant angular velocity, as I said.
Should I be thinking as this is the tube, the distance between, or just this is the thin tube, one thin tube with a distance between the two tubes?
There is some wrong, that not successful picture to your representation, but can you assume that there is a constant distance between the two?
We can, our theory allows us to use any spiral which is defined by a function.
Yeah, but you consider the Archimedes spiral, yeah?
Yeah, we consider.
Okay, and
Just for
you,
practical reasons for the experiment.
and you mentioned that the Archimedes spiral as a parameter here.
Yeah.
Like other parameters, number of turns, diameter,
Yeah,
the angular velocity, by your suggestion, the Archimedes spiral is also the parameter as a cube.
Yeah, it is parameter of our experimental apparatus.
Yeah. and the radius between the distance between the spark between the turns is also the effect on the if you have a water flux which look at something like that. If you will increase the distance between the turns, so it will be the increasing of the distance between these. Yes?
Yeah.
I share. I agree.
Yeah, I agree.
Yeah,
But that's with our theory allows us to calculate the end pressure for any spiral defined by a function. So each has
Okay,
no
yeah.
problem with calculating
Okay, that's
any
case
spiral.
we have a disagreement. Okay. So, and my next question would be about the experimental setup. Did you check the consistency of the angular velocity? Because you hear that if you will rotate the water plug, there will be the increasing of the numbers of the water plug into the spiral.
Sorry, I don't understand.
If you will rotate the spiral by the constant angular velocity, yes?
Yeah.
No, not constant angular velocity.
Rotating the
Just rotating the whisk pump, there will be the increasing of the numbers of the water plugs inside the spiral.
No, because they are going through the airlift and they are pumping out into the bucket that is at the top of the staircase. There is always the same, in any time there is the same amount of water plugs and air plugs in the whisk pump.
But I'm saying about the initial position when the spiral initially doesn't have any water plugs inside.
Yeah.
But after the rotation, there will be the increasing of the numbers of the plugs.
Yeah, we are studying this.
So yeah, and it will be the increasing of the mass, which also needs to be
we use higher amps for our motor, so it has no effect.
Okay, so can you show to us the 17th slide?
17th line. Okay.
Yes. So you said that there is no experimental evidence for these conclusions. Yes?
No, there is experimental evidence. We tried it. We
You
just
tried
tried it,
but-
and we found out those are the optimal tubes for our setup.
Okay, so our suggestion for the improvement.
Thank you. Yeah, you can continue in concluding remarks.
So okay, I want to say that the reporter has shown to us the very great amount of work, but there is some problems with the listing of the relevant parameters, which also need to be considered in the for the pumping height. So there is no checking experiments for the consistency of the angular velocity, and also there is the lack of the experimental number of the experiments for the comparison with the theory, and the lack of the explanation of the graphs on the positions that why the pumping height is brought down drastically, and the main problem of the report, I said that the main problem of the lack of the experiments for the comparison with the
Thank you. Please, clarifying questions?
Thank you for a insightful discussion. So let me start with this case. So can the report explain why does the trend of the theory look so high in a submersion depth of
Because where our theory is predicting our experiments, there are two water plugs in the tube, and the jump indicates the third water plug being able to be in the tube.
the third?
Third water plug.
Okay. And did you have any experiments on the maximum, the optimal submersion depth? So if you keep going to a higher depth with the experiments, would it also go down the theory?
Experimentally, we were not able to obtain a higher submersion depth.
So in your experimental range, higher depth means bigger height, right?
Yeah, but it's like really slightly because
Okay, thank you. And so to the reporter, so you mentioned the tube is 4 mm, correct?
Yeah.
So you assume that airlock effect is always true, right? So
Yeah.
Yeah. But in 4 mm tubes, in a vertical tube, we know this is more than a capillary length of it's bigger than a capillary length of 2.7 mm. So when water plug is inside, do you believe the water plug will drip down? Or the airlock assumption is always true?
it will be airlocked. We studied a paper which was investigating this phenomenon.
But
and
it's it's smaller than it's bigger than capillary length. It will not fall down in your experiments.
No, it didn't develop as an error as the experiment.
Okay, thank you. So the opponent, you mentioned you asked him about the length of the water plug. So do you think that the length of the water plug should be constant, in your opinion?
Should be constant.
Yeah, should
in
be constant.
the theoretical model.
Yeah.
I think not. No.
So it should not be constant.
Yeah, not be constant because there is an external pressure by the previous water flux.
Oh yeah, okay. I agree with you. So can you go to page 11?
Okay. Give me a second.
May I ask, how did you obtain Q? Pumping speed?
Our pumps pumps 1 water segment per revolution.
So this is the flow rate. Are you talking?
Yeah.
Okay, yeah, okay. Okay, in your viscous loss, how does the viscous loss? I don't understand why the viscous loss affects the height. So what is it? Friction? Is this the friction term?
Yeah.
And how? But the water plug positions are quite steady. Why is the friction significant?
They are not steady. They are moving and pumping up, and there is pressure loss because the water plugs are dragging altitude.
I do agree this affects in the vertical tube, but inside the water pump, I don't think this viscous pressure loss is that
But
significant.
the water plugs are moving in the pump.
And okay, let me ask final question. How do you determine your height?
Experimentally,
Measure. How do you measure?
we measure. We try to put in the bucket with the
Okay, thank you. Yeah, preparation happens. To start.
Okay. Hello everyone, I'm a reviewer from Team Taiwan with ring problem number 16, word pump. So this is a problem concept. So we want to explain the phenomenon and investigate how relevant parameters depending on the pumping height. Well, I believe the key question for this problem is about the pressure accumulation mechanism and how the hydrostatic pressure of each revolution stack up, which I believe the reporter explained quite well. And then the pumping conditions. So the maximum height, I asked about the reporter on how he collected the maximum height in the end. He said he used a bucket to find where the highest place the water could pump. But the more interesting part is we could see the height over time graph. I believe the process may be dynamic and maybe related to an angular velocity that the opponent is talking about. And about dynamic modeling, about the water plug not being static and the centrifugal force under big angular velocity. So here's a review of the report. So for phenomenon explanation, he mentioned the airlock effect, which is the alternation of air and water inside, which is a key mechanism. And about the airlift effect, so that's the reason why the burst pump could reach a greater height, because water, air is less than rho GH. and yeah, the hydrostatic pressure. So I believe this is very good explained on the high delivery height. But the report did not explain what causes the initial level difference. Because when the first water plug comes inside, the gravity should be uniform. So no hydrostatic pressure, no water level difference will form. I believe you need to explain why there will be a first height difference of a single water plug. And for the theory model, he uses the Boyle's law and Pascal's law to calculate the water plug inside the tube and add them up to actually get the maximum height. What I believe is very good that he uses the Boyle's law to account the compressibility of the air plug and calculated alternation of air and water, which he improved on the current references with the friction model. But I think the not good part is about you assume the water plug length to be constant. When I asked with the opponent, I believe the water length would not be constant because of the inside pressure. And about, we only have the static model, which I believe in real life, even though it's spinning slowly, the dynamic model which makes the dynamic height more interesting. Then for experiments, I believe he has only two parameters of the depth and the diameter of tube. I think it is good that he tested the limits for a tube, which is the 4 mm case and 6 mm case, where we find the 4 mm case to be the best. But I believe the 4 mm case is still bigger than the capillary length. So I talked about the water plug may drip down and not satisfying the airlock effect. And also, he has a smaller range of experiments, only 2 graphs, and did not find the maximum. So this is the same. So he only has a prediction of small range where he did not find the maximum and the theory deviation. Now here's the review of the opposition. So the first in a report talked about the limits of the theory of bubbling, which I agree, because you could analyze it with a Bond number, which could be analyzed how much bubbling is formed causing the pressure loss. Where in this discussion, they first talk about the explanation of the equation, what I think is quite good about the Boyle's law and Pascal law. But I believe he focused on too much non-reported parameters, which I think we should base on the reporter's work. So here's the next point. I believe the max height should increase with angular velocity, because as the water plug will drip down, if we can make the water plug travel with faster velocity, we can reach a greater height. And also, the air formation should be investigated with a Bond number. So here's the key discussion. So the reporter used the Boyle's law and Pascal law. Well, I believe these two equations have to satisfy a specific configuration inside a water pump to get the actual geometry results, which I think the reporter did a good job. Then, opponent asked a case about very high angular velocity. But I believe we should try to determine the max height under different angular velocity, and because I think it will reach a maximum. Because when angular velocity is too big, centrifugal dominates, which is not good. But obviously, some angular velocity will be good. And about the geometry, so I think it is, I agree with the reporter, our Archimedean spiral would be best because it has the best effective radius. And I talked about the capillary length causing the water plug to drip down and the water length being constant. I believe I agree with the opponent being constant. And yeah, thank you.
Thank you very much. And concluding remarks of the reporter, please.
I would like to thank the reviewer for his good points to the report, and I would like to state some final remarks. So, in the discussion, we discussed the tube diameters which were experimentally optimized, and I see no problem with this when we didn't experimentally find any bubbling of the air from between the bubble segments. We clarified the confusion about the angular velocity, and we are talking about the dynamic pressure, which I see irrelevant with 1 revolution approximately per 10 seconds. Then we had a spiral discussion, and I want to say that our theory can work with any spiral function, but we use the Archimedean because it is best for the experiments. I would like to say that we did a theoretical work that improved on existing literature, which I think is a really good thing. Where you can see that the theory from the paper doesn't predict our metadata at all, but our theory predicts it very well. Some remarks to the review. He talked about the hydrostatic model not being sufficient, but I believe that the hydrostatic model is sufficient and it doesn't need to be dynamic because of the low RPM and also I don't think that it is relevant to look at the maximum height in the time, because we should study pump that is pumping, not in a vertical tube, the maximum water level rising and going up and down.
Thank you. Yeah, questions from the jury? Who wants to go first? This time,
Yeah.
please.
Reporter, can you go on to slide number 17?
Yes.
Okay, can you explain why 4 mm had a problem with the collecting water?
Because when the 4 millimeter pipe was going through the water, it didn't have the water segment that is defined by the submergent depth. When you imagine the spiral like this, and here the water level, we are expecting the water segment of this line. But with the low diameter, that just didn't happen because the diameter was too small and the surface tension was working against this.
Yes, please.
Question to the reporter. You used Boyle's law for your theoretical model. Can you make sure that the conditions are fulfilled to apply that law?
We didn't check if the temperature was constant, but with the experiments were really slow with the 10 seconds per rotation, so we believe that the temperature stabilizes to the room temperature.
Okay. Yes, please.
Can you go to slide 20? Okay, why do I have a maximum height at the submersion depth equals 0?
Because the water segments are really small, so they create a really small pressure in the airlift. So, and in the water pump, they can align such in the best way because they are really small. So, due to the curve in the spiral, when we have long segment in the curve, the height isn't as effective as a really small curve in the spiral, in the term.
I think the open mentioned something about this. What is your opinion on the matter? Yeah, what's your opinion on this matter? Like,
I think you mean on the theory or experiment?
yeah, theory.
Oh, I think the theory is should be like a maximum. So in lower height, not the water plug length is so small, so barely any height difference of a water plug generates. And in a very deep, not enough air can be compressed to actually accumulate the height. So I think it will reach a maximum. Yeah.
Okay, thank you. Yes, please.
Question to the reviewer again. Correct me if I'm wrong. You claimed that the maximum height increases with increasing angular velocity.
This is because his selection of 4 mm tubes. So so if I'm not wrong, this will cause the water plug to drip down.
If it increases to infinity, then the water height.
No, because I think it will reach a maximum because in
Okay, yeah, thank you. Any more questions? Yes, please.
So can you put it on slide 19? So yes, you have that tube diameter already mentioned. Okay, my question is that does your model hold true for all kind of pipe diameters?
No, because we assume that the water lock is true, and that is true only for small tube diameters. So if the water lock is true, our model works.
Okay. Yeah.
Thank you. If no more questions, we can go on.
Just one
Yes.
more. Okay. You have angular velocity, right? And you say that you use a motor to. You have the calibration of this motor, like.
We were spinning it and we filmed it to get the angular velocity.
Thank you. Yeah, we can move on to grading. No more questions. Yeah. Is everyone ready? Okay, perfect. Yeah, just before we show you the grades, do not forget to submit your preferences for round 5. You should submit 3 problems according to your preference. Yeah, you all have the sheets for submission, right? Okay. Yeah. Okay. Let's show the grades for the report. Is 4, 3, 4, 5, and 5. Grades for the opponent. It is 5, 6, 5, 4, and 4. And grades for the review. 8, 7, 7, 6, and 5. Okay, for the report, which you have 3.
Okay. You say that you improve theory, and I after this fight I don't know what was the theory that you improved. I really don't know. And when I looked at this graph, and you only have data from 10 to 30, I don't know if your model is a good model. And you say in your final remarks that it works for any spiral, and then in the question, your question, you said, oh, for this kind of pipe, it doesn't work.
Yeah.
So you say 2 different things, and this for me is a problem. I think you explained the phenomenon, but I don't agree too much with your theory and your experimental. You don't get a graph for height in function of the number of spirals, the angular velocity, angular speed, and I think it could be more careful with these parameters.
Thank you. And on the higher end, we have Shashkinator Otmar. So,
maybe for the
yes,
5,
please. Yes, please. Yeah.
Like your relaxed presentation style. Nevertheless, I had to criticize all of you. If you increase the pumping at angular velocity, then Boyle's law isn't valid anymore, because it's more an adiabatic process, well, and therefore justified.
Yeah, that's when I agree to so integrate with as well. Okay, let's move on to the opposition. We have low grades of 4. Yeah, maybe now we can comment.
Yeah. Okay, so I didn't find any scientific contribution to this discussion. Basically, throughout it was the same point again and again it was discussed. So I just gave a grade of like 1 for asking questions, 1.1 for having a speech, no, 1.1 for the speech, and 1.1 for again for discussion, which rounded up to 4. There were many points for discussion, and he just pointed again on the rho GH or P1, B1. Those are 2 points where he wasted a lot of time. I thought basically we should have discussed more beyond those aspects.
Okay, thank you. And we have Luis on the higher end of the opposition grades.
I kind of agreed with you, but I think that was an average discussion at all. I think that you said, okay, you didn't vary the angular speed, and you can show me or a graph in the. You can draw me a graph and show me what you think about this, making more your opinion about this parameter variation. So I think that was an average discussion.
Thank you. And now finally the grades for the review. Let's start from the lower.
Yeah, that was my 5. to the review. It's a question how to estimate the problem, the pumping height. Is it a dynamic process? Of course, it needs some time to exceed a height. That it should be a maximum height, and there might be some dynamics for oscillations in that maximum height. Nobody talked about that. But in my opinion, maximum height, it's quasi-static, and then something doesn't fit with each other. You didn't find out also about this Boyle's law, and there were some lacks in your reviewing, and therefore justified.
Yeah, on the higher end, I think like for this fight I have been a little bit higher on the review end, but I really liked your review, especially like the starting with the clarifying questions. You brought in some like lots of extra things, and what is the main point that you had your opinions mostly correct about like the physics. You even managed to persuade the reporter about the importance of the angular velocity and what would change. Plus, yeah, and then you had a very detailed discussion analysis of every point with your own opinions presented. Which were basically important. And yeah, and some points as well. So yeah, that is why I went. Yeah. Okay, if you have any questions, yes, please.
Jury said that there is no mention about the instability of the pumping height, but in the slide have mentioned about it and as a areas for the upcoming counterorder.
Okay, thank you. Yeah. Yeah, for example, I remember that when I mentioned about the pumping height and the angular velocity, I mentioned was reviewer and opponent that pointed it out. But like, reviewer pointed out it much more clearly. You did not manage to persuade the reporter in the discussion about it. Yep. That's basically it. So thank you very much for this great fight. Yeah, well, finally, once the day is over, and yeah, please like submit the preferences for rounds 5 right now. Everyone is already written it down. Yeah, do not leave the room before you submit the preferences.